this is Mrs. Marita. Welcome to AP Stats, Lesson 12.3b. Our learning targets for today are 3 and 4. Construct and interpret a confidence interval for the slope beta of a population regression line, and perform a significance test for the slope beta. The first inference procedure we're going to work on is a confidence interval for a slope beta. When we construct our LSRL, the y hat equal to a plus bx, and conditions are met, b is just an estimate, our statistic, so an estimate of the true slope beta. We can create a confidence interval for the true slope using the formula b plus or minus t star times SEB, where t star is our critical value and SEB is our standard error of our slope. Our degree of freedom is going to be n minus 2. That's going to help us find our t star. 12.3, Example 3. Recall the Example 1 review problem, does seat location matter? Below is computer output provided for this question. We want to construct and interpret a 95% confidence interval for the true slope beta, following our 4-step process. When asked to complete any inference procedure for our true slope beta, the first thing we want to do is cross off these 3 values in the top. We're never going to use those. We also want to cross off the r-squared adjusted value. Everything that's left, we might use. Recall that your constant is a, your intercept, and your rho, or the variable they give you, this value will correspond to b, your slope. Your s is your standard deviation of the residuals. They are also providing you, this is our r squared, RSQ is our r squared, and this is our standard error of b, standard error of the slope. Next is going to be t and p. Well, p, this will be our p value later, but careful. This value t, this is your test statistic. This is only for a hypothesis test. This is not t star. T star we're going to have to find using inverse t like we did before. So make some notes so this is helpful for you later when you go back and review your computer output. Let's move on to our 4-step procedure though. We want to construct and interpret a 95% confidence interval for beta following our 4-step procedure. First, state. We need to define your x and y variables and beta. You can define all of these individually, but if you want to combine it into just one run-on statement, we'll define beta as the true slope of the population regression line relating, and now we'll define our x and y. Y, the student's test score, to x, the row number a student was assigned to. For our plan step, we need to check our conditions, all 5 of them, but we already did this on page 263. This is just a continuation of our previous example. Next, our do step. We want to show our formula, substitution, and answer to come up with our confidence interval for beta. Our formula we were given above, this is our b, the statistic, plus or minus the margin of error. Our margin of error is our t star times SEB. The b and the SEB, our standard error b, are both provided to us in the computer output above. But remember, the t in the computer output is not your critical value. That's a test statistic. Our critical value t star, we're going to find the same way we found this back in our previous chapters. To find our t star, first we'll state our degree of freedom, and for bivariate data, our DF formula is n minus 2. So we ended up with 28 for our DF, and then we go to our calculator and use our inverse t. Recall that's your second bars, same place that you found your normal CDF, binom CDF, all those CDFs. Your inverse t and inverse norm are also there. So we plug in 0.975, that's the area below. And then our degree of freedom, 28. Remember, even though our confidence interval was 95%, if we visualize our 95% confidence interval, we have that 0.025 area in the tails. So the area below our t star, this area is 0.975, the 95% plus the 0.025. That's where we're getting 0.975. So we can plug in to 0.0484 and then continue to crunch this out to get our final answer. If we work out that product on the right, we get about 1.94. And then we'll take negative 1.1171 minus 1.94, and we get about negative 3.0571. To get the upper bound, we're going to take our negative 1.1171 and add 1.94, and we get about 0.8229. For these confidence intervals, we actually have to work this out when they give us computer output. If they gave us data, we could utilize the test function on our calculator and do a regression inference procedure there. But if they don't give us data, if they just give us the computer output, we're on our own. We just have to multiply and subtract and then multiply and add. On your AP exam, you'll most likely be given computer output for problems like these, so this is what we're going to practice the most. Last step, our conclude. Even though our parameter beta is new, this wording should sound familiar. We'll say we are 95% confident that the interval from negative 3.0571 to 0.8229 captures beta, the true slope of the regression line relating a student's test score to their row number. 12.3, example 4. Do customers who stay longer at buffets give larger tips? One student who worked at a buffet-style restaurant decided to investigate this question. This is our last learning target of the course, LT number 4, perform a significance test about the slope beta of the population true regression line. Let's look at the student's investigation. While she was doing her job as a hostess, she obtained a random sample of 12 receipts, which included the length of time in minutes the party was at the restaurant and the amount of tip in dollars that they left. Below are several graphical representations provided as well as computer output. Do these data provide convincing evidence that customers who stay longer at the buffet give larger tips? Just a flashback. When we're trying to determine whether the problem is asking us to perform a confidence interval or a hypothesis test, there's going to be some clues we look for. With a confidence interval, you're going to be asked to estimate a parameter. With a hypothesis test, like this one, they're asking if the data provides evidence of some result. Just like in our previous example with our computer output, we're going to cross off these 3 top values. We'll never use those. And label what we do know. We'll cross off the R-squared adjusted 2. Now we're going to get into our t and p value. Remember, this is going to be my p-value, and the t-value here is my test statistic. We'll need to use these graphical representations for checking our conditions. Let's jump into our 4-step procedure. First, our state step. So we'll say beta is equal to the true slope of the regression line relating y, the amount of tip in dollars, to x, the time at the buffet, in minutes. That part of the state step is the same as we did for the confidence interval. But now we need to state our hypotheses and our significance level. As always, if they don't give you a significance level, use 0.05. For our hypotheses, our null hypothesis will be that beta is equal to 0. If beta is equal to 0, we're saying that our true slope is equal to 0. And remember, a 0 slope is a horizontal line. So this hypothesis means that as your x value changes, there's no change in the y value. That's going to be our no change, no relationship, is when your slope is equal to 0. For the alternative hypothesis, just like before, we'll use the same parameter beta and choose either a greater than, less than, or not equal to. Because we think that if somebody stays longer at the buffet, they might tip more, our alternative hypothesis will be a greater than 0. This is hypothesizing that we have a positive slope. Next is our plan step. First, we need to mention what type of test we're doing. For this example, we're looking at a t-test for slope. In the past, we've done a t-test for means or a z-test for proportions, so this is similar, but we call it a t-test for slope. Our first condition is to check our scatter plot. We're going to say, yes, the scatter plot shows a linear form, so this linear condition is met. Next, we need to check for independence. We're going to check if our population size is at least 10 times greater than our sample size. They gave us in the stem of the problem that we looked at 12 randomly selected receipts. So we can say, yes, we can assume there are more than 120 customers. Third is our normal condition. In this example, the graphical representation they gave us was the NPP. The NPP here is approximately linear, so we can assume our sampling distribution is approximately normal. Fourth is the equivariance condition. For this one, we look back at our residual plot, and we can say that our resid plot shows random scatter. And last is our random condition, and we can just say that we're given a random sample of 12 receipts. That was provided to us in the stem of the problem. Now on to our do step. Just a reminder, there's 2 parts of our do step for a hypothesis test. First, we need to show our test statistic, then our p-value. The formula for our test statistic is your statistic minus your parameter all over the standard error of your statistic. So in this example, t is equal to b minus beta all over SEB. These values were provided to us in the computer output. Our statistic b, the sample slope, was 0.03013. Beta comes from our null hypothesis. We're hypothesizing that beta is equal to 0 until we prove otherwise. And then SEB you can find in your computer output. That's the 0.02448. You can work this out, but they give us the answer in the computer output as well. So we could just state that our t is equal to 1.23. Next is our p-value. Our p-value we're just going to pull down from the computer output as well. So our p-value is equal to 0.247. That's kind of a big p-value. Time to conclude. So in conclusion, we'll do our stat talk first. The p-value is equal to 0.247, which is greater than 0.05 our alpha level, so we fail to reject our H naught. And then our context, we do not have convincing evidence that there is a positive relationship between the time spent at the buffet and the amount of tip. The important detail to add is that we're not convinced that there's a positive relationship. That's where we're bringing in our alternative hypothesis that was a greater than. So a positive relationship would correspond to a positive slope. That's what we were testing for with our HA being beta greater than 0. But because our p-value was large, we do not have convincing evidence that that is true.